Hello.
Hello.
We can hear you.
Perfect. So we will start in 2 minutes. Let's wait for another 2 minutes. I think we should get started now. So hello everyone, my name is Dhruvin Patel. I'm from Ericsson Research, Germany. So welcome to the webinar of 5G TSN deployment models and time synchronization aspects. Today's webinar will be presented by Dr. Krister Landernäs, who is a technical manager of 5G Smart, Dr. Joachim Sachs, who is a senior expert from Ericsson Research, Sweden, and Dr. Daniel Philip Venmani from, who's a senior research engineer from Orange Labs, France. We can go to the next slide. So before getting started, a couple of things that I would like to highlight. The meeting is recorded. This includes also the question and answers during the talk. This is an interactive webinar, so if you have any questions, please feel free to ask during presentations via chat. Please, I will request you all to mute yourself if you're not talking. The materials, including slides and the recording, will be made available afterwards. So, without wasting any time, I would like to hand over the floor to Krister. Krister, are you online?
I am. So
yeah, perfect.
Okay. Good. I'll take it from here then. So I will give a short introduction just to put things into the context, and then we will discuss the topics that you see there on this slide. But if we go to the next slide. Right. So just a couple of slides from my side to again put things into context. I think everyone on the call is aware of the transformation that is going on in industry, moving towards Industry 4.0, and all the aspects that will change in industry, anything from business models to technology, services, etc. And 5G, of course, has a large role here to play. If we go to the next slide. 5G Smart, for those of you that don't know, is a European Horizon 2020 project where we look into 5G for smart manufacturing. The focus is on industrial 5G trials, and we have 3 trials in the project. So one at an Ericsson factory in Kista, Sweden, one at IPT Fraunhofer in Aachen, Germany, and then one at a Bosch factory in Reutlingen, in Germany. And we also have activities around business models and network deployments, as well as more technology-focused activities where we look into how to enhance and further improve 5G for smart manufacturing. Next slide, please. So this is an overview of the 7 use cases that we will implement and trial at our test beds. And as you can see, they cover and span different industry domains. And if you want to know more, just follow the link at the bottom of this page. Next slide, please. Coming back then to the transformation and looking at it from a connectivity point of view. So what is it that we want to achieve? Well, we want to simplify and harmonize the industrial networks, making them more flexible, making them more transparent. And then 2 technologies that we think are key enablers in order to succeed here are TSN and 5G. And of course, it's very interesting then to see how these 2 technologies will integrate in an efficient way. So with that introduction, I will now hand over to Joachim to give us an introduction into that topic.
So can you all hear me? I hope so, at least it worked before. So I will be starting with providing a brief introduction into TSN. Now, where's my pointer? So when we think of what is TSN? So TSN is a set of IEEE 802 standards for deterministic data transfer for layer 2 bridge networks. And the specification happens in the IEEE 802.1 group, which means it's a standard that benefits from all this open IEEE standardization process, and it and builds on the standard Ethernet that is being specified in the IEEE 802 group. What the focus is to bring in this deterministic data packet delivery, which means having control, as you see here on the right-hand side, on when packets are being delivered. So you can give a deterministic guarantee on delivery of packets. And as I said, it's in bridge network, so it's on the lower is the data link layer and physical layer where this standard applies. When we think of what is TSN, it's actually a toolbox of different components, and there's a set of standard amendments regarding time synchronization. There's a set of standard amendments on providing high availability and high reliability. Another set of standards which improves the capability to bound latencies to achieve low latencies, and a set of standards defining the configuration and the resource management. So I won't go into the details of this, but simply to say TSN is actually a toolbox of individual components. And then there are activities that are defining profiles. For example, finalized profiles are for audio-video bridging and front haul in cellular networks where TSN is being used. And there are 3 profiles which are work in progress: service provider networks, automotive in-vehicle communication, and industrial automation, which is specified in a joint group by IEC and IEEE. And these profiles basically defined how this tool that we see down here at the bottom is to be used in these specific application contexts. So the profile of industrial automation basically sets the requirements. If you want to use TSN in industrial automation, what are the tools that should be supported out of this standardized TSN toolbox? I go through some of them on high level. So the one central part of TSN is the configuration of the TSN communication, which is specified in 82.1 QCC, and there's a centralized configuration that has been where the standardization is finished. There are also distributed models where the standardization is still ongoing, and there's a central user configuration which basically provides user and network configuration information of the data streams to be transmitted. And there's some application-specific kind of relationship between this centralized user configuration and the actual applications. The centralized network configuration is basically the central controller in this TSN network, which obtains the information about all the TSN streams in the network and then can configure, and it receives also information about the bridges and the network topology, and it configures based on the requirements of the applications the network with the corresponding TSN features. What TSN also introduces is the distribution of time synchronization over the network, so that different TSN switches can be synchronized to a common clock, as can be the end applications. One feature of TSN is to specify traffic scheduling, which is specified in IEEE 802.1 QBV, and that is basically where on a per switch basis, the CNC configures circles that a bridge at its transmission can reserve different parts of the time, for example, for transmitting prioritized data streams or TSN streams, and then there are other time slots for best effort traffic, for example. And by doing this over the network, it is basically possible to coordinate the schedules of bridges along a path for being able to configure, for example, very low latency paths throughout the network by coordinating the schedules that are put in place in these different bridges along the path. Another functionality for reliability is specified in IEEE 802.1 CB, which is reliability for which is frame replication elimination for reliability, where a TSN stream can be split into two redundant variants, which can be transmitted over two disjoint paths, and at a reception point they can be merged together again. These are some examples of the tools that TSN provides in an Ethernet bridge network. There are more tools like per stream filtering and policing, preemption, and so on. But this basically gave a high-level overview of some of the key functionality of TSN. The question is, so now what of these functions are needed for industrial automation? And their industrial automation requirements are addressed in different groups. There's the standardization group for the industrial automation profile. There's, of course, the standardization group itself for TSN. There's a TSN testbed group in the Industrial Internet Consortium. There has been work around this in the on the service requirements in the 3GPP standardization. There's also been work related on this in the 5G ACIA Alliance for applying 5G for industrial automation, which actually yesterday published also a white paper on 5G support for TSN. And out of all of this work, there was this table provides a summary. And this is not yet specified, so it's a little bit an example because this is ongoing discussions in these different groups. But what you can see is that there are different types of traffic that play a role in industrial automations, from real-time control, which can be synchronous or asynchronous. There can be alarms. There can be diagnostics data. And there's, of course, also best effort data. And towards the right-hand side of this table, we see the recommendations on what functionality for Ethernet TSN are given. And when we look into this, one important part is that prioritization of different traffic classes is a mandatory feature. The central configuration of the network with this QCC, with the centralized network controller, is an essential part. The policing, per stream filtering and policing is an essential part. And then the redundancy is considered as an optional feature. And time synchronization is together with this time-aware scheduling is needed for these synchronous operations. But it should be said here that the time synchronization here is described from the perspective on how to activate the TSN feature, which is in this case the 82.1 QBV time-aware scheduling. But beyond that, time synchronization is in general required over industrial networks for the purpose of providing time synchronization to the applications. And later we will have there are different parts of communication in the on the shop floor that I will come back to a little bit later. But this shows a little bit how the relationship of these traffic streams is. And some of these are a controller to device communication, where the controller, for example, is connected to IO devices or sensors and actuators. Coordination among different controllers, so controller to controller communication, or device to compute communication, where devices provide collective insights that are analyzed then in a backend. So this gave a brief overview of TSN and applied to industrial IoT. Now I will say something about 5G, starting with the standardization view. 5G was specified in the first 5G standard is in release 15 of the 3GPP standard, and there the introduction of the ultra reliable and low latency communication was introduced. Also, the support for Ethernet data transmission over the 5G system has been introduced there. Release 16 is the second release of the 5G standard, and that was finalized last year. And what was introduced is enhancement to ultra-reliable low-latency communication in 5G, but also the support for TSN and LAN services has been explicitly added in this release of the standard. What has also been added is the support for non-public networks that I will touch upon in one of the coming slides, and timing as a service from the network to the UE, so that you can have a reference time that is provided over the 5G network to a device. And we will have a lot of more information on this in a later part of this presentation. Now, the work on release 17 is ongoing. So there are some enhancements on time-sensitive communication. Also, the time synchronization is enhanced so that now the reference clock does not need to be on the network side, but can be on a device side, and we will hear more about this later. And this is the ongoing work where the conclusion, there are some uncertainties due to COVID, exactly how the standardization schedule will develop, but it is expected that in 2022, this standard will be ready. Right, now these non-public networks have been introduced in release 16, and the non-public network is a network that is intended for non-public use, which means it's also restricted to authorized devices. There are a couple of variants of such non-public networks. It can be, like we see here on the left-hand side, an isolated non-public network, which means, for example, if we have an industrial site, you deploy a dedicated 5G network only on that site that is basically independent from any other network. If you wanted to have some interworking with a public network for roaming or whatsoever, this could be arranged, but it goes basically via firewall, and it's an optional connection. Other options of providing a non-public network is that there are some commonalities with a public network, which can be that, for example, there's a RAN sharing, as it says, which means the radio network sites are used at the same time for providing connectivity to the private network, here depicted in blue, and the public networks, which means users which are public network users use these antenna points to connect into the public network, and private users connect into the local network. There are more options of this sharing where, for example, even the management and the control of the network operation can be centralized and can be provided as a service for the public network, and only the data plane, which means the user data, is basically routed locally. And in another option, it can be that the non-public network is basically provided from the public network operator as a service towards a dedicated device group. So there are different variants of how such a non-public network can be realized. They have been also summarized in a white paper of the 5G Alliance for Connected Industries and Automation. And the link is there, and you will find it later in the references as well. Now, when 5G is integrating with TSN, we have now an industrial side where we have a TSN network, here depicted in orange, and now we put a 5G system into the same setup. The way on how this interworking between the 5G domain and the TSN domain happens is via some extra functions, which is in the control plane. It is the TSN application function, which provides the interactions towards the TSN controller, so the centralized network controller. And it configures then also the 5G connectivity according to the needs of the TSN streams to be transmitted. On the user plane, we have the so-called TSN translator functions, one on network side, a network TSN translator, and one on the device side, a device side TSN translator. And they provide then the user plane TSN functionality. Now, to look into how this is being used in a practical example. So we take now one of the use cases that we study in 5G Smart, and we start with thinking of an industrial controller, which typically today you have a controller which is connected over a cable, typically with some real-time communication protocol like some field bus to the robot, and then the controller is controlling the robotic operation. By introducing TSN, it is now possible to put this controller somewhere else and use the existing communication infrastructure, and making a configuration that this particular controller to device communication is provided with high reliability and low latency, so that all the demands on real-time capability are provided even if there's a larger network in between. Which means we can go away from a very dedicated local field bus network and can make use of a more generalized communication infrastructure. This provides the benefit that the controller can be more easily moved to another place, like a dedicated room or where an edge cloud could be located. And this provides the benefits that the robot can become lighter and smaller, occupies less floor space. But it's also possible to have a better maintainability. If we have, let's say, 100 of these robots in a shop floor, then the controllers are basically all in the same room, and they are maybe even virtualized in a cloud environment. And it's easier to realize cooperative tasks across multiple robots. What can also be done is that this can be enhanced. For example, there could be a video system which is being installed and which is connected to a cloud-based machine vision and machine scene analysis logic, which can be connected then to the controller, which means the controller can be enhanced with these additional, let's say it's enhanced sensor system, which can more easily provide new algorithms and to the control of the robot. And then you can also say, well, if we have this control, we can take the state out of the status of a robot and monitor it in a digital twin, for example. And then we can have someone on the shop floor who can get access to the status of such a robot by connecting, for example, with AR glasses as some more future-looking human-machine interface into what is the task of this robot, what's the productivity, and adding this, well, basically observability of the status of the shop floor. And of course, by bringing in 5G communication, we add a lot of flexibility on how this connectivity is done. The robot can be mobile, the AR glasses will anyway be mobile, which means 5G provides enhanced deployment flexibility compared to cable TSN. This is a use case that we investigate in the trial setup that Krister mentioned at the beginning. So in the Ericsson factory in Kista in Stockholm, together with ABB providing the robot control logic and the robot arms. But we have also two other trial systems where I don't, due to a lack of time, I cannot go through these use cases and develop their, for example, the relevance to TSN now. But this can be done in a similar way for connecting, for example, a fleet of automated guided vehicles or autonomous mobile robots, where we put the logic of the vehicle into an edge cloud and enable then commonalities in developing, for example, a common map among them, or having control to control communication. And in another use case that we investigate in Aachen, what we do is that we have a machining process where we put additional sensors into the machine so that during the production, during the machining, we have sensor data which provides in real time observation of how the machining works. So for example, in a milling machine, this is what we investigate, and where you can see by acoustic emission sensors which that you analyze if resonances occur and lead to a risk that that there are maybe damages in the machining process. And we have a real-time analysis of this and feed it back into the controller of the machining process. So these are some use cases. Each of them have a relevance where the benefit of providing this general communication over a TSN-based infrastructure and 5G as a wireless extension makes sense. Now, when we look into these 5G TSN deployment use case and think a little bit, how does 5G provide this connectivity now? Then I assume that most are available a little with the general structure of a 5G network or a cellular network. There's a core network and there's a radio access network. The radio access network with many antenna points basically provides the coverage in the entire shop floor and is connected to a core network where we have gateway functions, the user plane functions, and we have a control plane and control functions for the entire 5G network. And it's mobile devices or user equipments in 3GPP terminology, which connect then to this 5G network. Now for the interworking with the TSN domain, we have these TSN translator functions and the TSN-AF that I introduced before, which basically provide the interworking to the external TSN network. And how the 5G standard has been defined is that basically towards the TSN domain, this 5G network appears as a set of 5G TSN bridges with the TSN translators and the TSN-AF as the reference points towards the outside world. And these bridges are defined in such a way that they have fixed ports on the network side. So they have network side ports here, and here's one here. And they have device side ports. And something which is very unusual for a bridge is these ports can be mobile. So we can have here a guided vehicle, for example, which can be moving around the entire shop floor, and still it provides a port to this bridge even while it's moving. So in total, there can be actually a larger distance between the ingress and the egress port of such a bridge. One device can be part of multiple TSN bridges by providing connectivity to different user plane functions of the 5G network, and thereby becoming logically part of different bridges. And in order to handle the traffic, TSN has its own way of handling traffic. So applications basically mark a different traffic type with a priority code point, which is a priority value. There are 8 of them specified in the Ethernet standard or the VLAN standard. And when they arrive at a bridge, there are ingress ports, and a bridge is capable of handling multiple traffic classes. If it handles 8 traffic classes, every priority code point is mapped to one specific traffic class. If it's fewer than 8 traffic classes, there's a certain mapping of priority code points to traffic classes. And then the TSN configuration specifies the traffic handling per traffic class. And in the ingress, there's even some TSN configurations for this filtering and policing, which is on a stream basis. And in that way, it's possible to configure basically quality of service and prioritization throughout a TSN network by making this configuration for each of the bridges. The 5G system on the right-hand side has its own way of handling mixed traffic and quality of service. A PDU session is let's say it's the connectivity that is built up between a device and the gateway function, the user plane function. And in such a PDU session, there can be multiple quality of service flows, and there are filters which specify which traffic flow is basically mapped to which of these quality of service flows. And then there's a configuration on the traffic treatment for all the traffic in one particular quality of service flow, like the priority, what reliability level this traffic should have. There can be latency configurations. And for time-sensitive quality of service flow, a minimum and a maximum latency can be determined. So in the interworking of TSN with 5G, the TSN application function interacts with the centralized network configuration of TSN, and it provides the capabilities of the 5G system as a bridge or a set of bridges towards the CNC, which like bridge and port information, the bridge delay, and it receives from the CNC traffic forwarding rules as well as traffic handling priorities, which means the configuration on how the quality of service for different streams is to be handled. And then it's a part of the 5G system to translate this configuration that it receives from the CNC and translate it into 5G specific mechanisms for setting up the corresponding connectivity in the 5G system and doing an appropriate quality of service mapping, which means defining the traffic filters at the ingress, at the device, and at the network side for what traffic is put onto which of the quality of service flows, the prioritizations, reservation of resources for flows, and configurations for reliability and latency. What is also being introduced is the time synchronization over the 5G network from a reference grandmaster clock to other network to other device clocks that are synchronized to this grandmaster, and we will have more information on this later, so I go over this briefly. For the specific handling then of the traffic handling, like the traffic scheduling and the per stream filtering and policing, this is received at the TSNAF from the CNC, and there are mechanisms standardized in 5G on how this information is provided to the TSN translators on the network and on the device side. And the realization of the QBV and QCI is then handled in these TSN translator functions. A hold and forward buffer is also defined for compensate for jitters that are introduced, or to limit the jitter that is introduced by the 5G bridge. And from the information that is provided from the CNC in this QCI profile, from that it's possible to derive information about the traffic characteristic as they are entering, the TSN traffic characteristic entering the system. And this information is put into so-called time-sensitive communication systems information, which can be provided to the radio part of the 5G network, so that there can be some radio resource optimizations, which is matching the profile and the requirements of the traffic. It's also possible, I mentioned at the beginning, that TSN introduces the introduction of these, it was called FREYA, of these redundant paths, and 5G allows to set up redundant paths and mark them as redundant in order to avoid that two connections basically get, so to ensure that they have disjoint paths, and then it's possible to map such the redundancy of streams in the TSN domain to these redundant PDU sessions. And with that, I provided an overview of well, what TSN is and what the 5G support for TSN is. And we will continue now with a little bit more details in the description of the time synchronization over 5G. And this is now Daniel who will continue with the presentation here.
Thank you, Joachim. Hello, everyone. My name is Daniel Philip Venmani. And from now onwards, until the end of this presentation, I will give you an overview about time synchronization. That is how timing is very important in the context of industrial internet. I represent Orange, a mobile network operator. So the goal for me here is to present how a mobile network, that is the so-called 5G system, can be useful in order to collaborate with the TSN domain. Joachim presented so far all about TSN domain, the various TSN standards and how they are useful within the TSN domain. But the entire goal of the 5G Smart project is to make use of the 5G system in collaboration, in coordination with the TSN domain. So moving forward, next slide. Next slide.
I'm on the next slide. Do you mean this one? Can you see it?
I don't see it. Yes, fine. So in this regard, we have identified certain use cases that shows why we need synchronization, especially time synchronization in the context of industrial Internet of Things. So like I said, TSN is a domain, time-sensitive networking is a domain, and mobile networks, cellular networks, the 5G system is another domain. We are now going to understand how the 5G system can be useful to transport timing packets from the cellular domain to the TSN domain. We are going to understand how the cellular domain could help synchronize a TSN domain. In this context, we have identified some major use cases. This is non-exhaustive: industrial control, industrial communication, industrial measurement. These are some of the major use cases that we have identified that requires synchronization. Any use case, any scenario which requires some level of coordination, some level of joint processing with respect to a common reference, especially with respect to a common time reference, requires synchronization in time. I'll take the first example, support of industrial control. So this could be, for example, different robots inside an industry. The robots can do anything. Here we have indicated welding station, but they can be inside a BMW car manufacturing company where the robots are used to align a car. And as you can see, these robots have to be aligned to each other with a perfect precision. In order for this to happen, you need these robots to be aligned to a common time reference. And in order for this to happen, you need synchronization, especially synchronization in time. So these are this is why we need time synchronization. Moving forward, next slide. So, so we have in this slide, we have identified the accuracy requirements from a standards perspective. 3GPP so far have identified certain use cases which require time synchronization, and 3GPP has also identified the accuracy requirements for these use cases in release 17. So there are 5 different categories. As you can see, it starts from 50 microsecond and it goes to 900 nanosecond. 900 nanosecond is the most stringent timing accuracy requirement that is identified so far today in the market. So this is the highest requirement that you need to take into account while you are going to transport timing packets from a cellular domain, from a 5G system to a TSN domain. What is also important to understand here is that this 900 nanosecond should be taken into account with respect to the service area as well as to the number of devices within the service area. Because we are talking in the context of industrial Internet of Things here, it means an industry. And within an industry, you are bounded to the number of robots, for example, present inside the industry, as well as the size of the industry. So, for example, the first category, the most highest stringent category, refers to motion control, that is control-to-control communication for an industrial controller. Here, 3GPP has set 300 UEs to be present in a 100 by 100 meter square area as 900 nanosecond. That is to say, if the number of UEs is, for example, 500 UEs, and the service area, let's say, for example, is 200 by 200 meters square, even if you supply 900 nanosecond accuracy towards this service area, it will not be able to synchronize the robots within the service area. So while you are looking into accuracy requirement, it is also equally important to look into the number of user equipments present in the service area as well as the geographical surface of the service area in the context of industrial internet. So this is the key message of this slide. Moving forward, the next slide. So, and therefore, as I said, now we know why do we need time synchronization and what is the accuracy value that has to be supplied for different use cases. Now, here, like I said, the goal is to see how the 5G system can support the transport of timing packets towards the TSN system. That is how the 5G system can help synchronize the different robots present within a TSN domain. Like you see in this figure, the black box, which has a user equipment, a G node B, a UPF, represents the classical 5G system. On both sides, you see TSN systems. This could represent different industries. It could be an industry, it could be a factory from ABB, it could be a factory from Bosch, it could represent anything. The goal now is to transport timing packets from the 5G system towards the TSN system. In order for this to happen, like you see within the box, you have a 5G GM. It represents a grandmaster, which is nothing but a primary source of time reference. It's nothing but a device which will receive GNSS signal and transport it towards your end equipments. Here, the 5G system should transport timing packets towards your TSN system. Because we have 2 different domains, that is the cellular domain, the 5G system, and the TSN domain, which is the TSN system, they are different. You need to translate the timing packets between these 2 systems. That is why on both ends, you have 2 devices which are named as DSTT and NWTT. DSTT refers to device side timing translator, and NWTT refers to the network side timing translator. These are nothing but a piece of software that can be embarked at both ends in order for the 5G system to collaborate easily, in order for the 5G system to transport the generic PTP packets towards the IEEE enabled PTP packets of the TSN system. So this is how, in general, from an architecture perspective, the 5G system collaborates with the TSN system. Moving forward, next slide. We have elaborated the previous architecture more into detail with multiple TSN domains on both ends. It is the same figure that you saw previously, except in the middle, you have the 5GC, which represents the 5G system. And on both sides, you have NPNs, which are nothing but non-public networks, which encompasses the TSN domains. What is also different in this figure is that the NPNs, that is the TSN domains itself, can have their independent individual 5G cores, which is what you see here. The UPF 5GC in green color, and on the right-hand side, the UPF 5GC in purple color represents the independent customized 5G cores which are present inside the NPN domain. But this does not change the way how timing packets are transported towards the TSN domain, towards the NPN domain. What is tried to show here in this figure is that the 5G system can make use of the 5G RAN, the 5G NR, in order to transport timing packets, not just to one TSN domain, but multiple TSN domain, which requires dedicated 5G cores. For example, this is the key message, and this could also be done in the context of 5G time synchronization. Moving forward, excuse me. So I have given you an idea about why do we need time, what is the requirement, and how the 5G system can be helpful to transport the timing packets towards the TSN domain. Now we are going a little bit into detail. First part is we wanted to see what happens, what is the real thing that is going on inside the 5G system itself while we are trying to transport the timing packets towards the TSN system. So we are zooming closer into the 5G system, the black box, which contains the UE, which could be anything. A UE can be a smartphone, or UE can be an equipment, a router, which is just going to transport your timing packet. Then your G node B, the NR, and then the UPF. Between the G node B and the UPF, you have the 5G transport network. And on both ends, like I described, you have the device side time translator and network side time translator. And all of this receive a common time reference from the 5G grandmaster. So while you are trying to transport timing packets from the 5G system towards TSN, there are two things that are needed to be taken into account very importantly. The black arrow mark, which says time sync over transport network, and then the green arrow mark, which says over the air radio time sync solution. As a mobile operator or anyone who is going to transport timing from your network to another network, you need to make sure that these two criteria, these two constraints are met. The first one, the 5G grandmaster sends a timing packets towards the G node B. This could be a direct link sometimes. So the G node B receives the timing signal, the timing packets. It now has to send it to the network side time translator because there are TSN domains on the right-hand side. When you do this, you need to make sure that the 900 nanosecond that I described is met between the G node B, or no, between the 5G GM, G node B, and the UPF by the number of equipments which are present between the G node B and UPF. Normally, I say 5G transport. I'm not going to get into the details of it, but you see G8275.1 is an ITU-T standard that defines how many equipments should be present, how timing packets can be transported over a 5G transport network. So that is defined there. The next part is the left-hand side, the green arrow, how a G node B is going to transport the received timing packets over an UV. The difference between the green arrow and the black arrow is that the right-hand side is wired networks, and the left-hand side, the green arrow, represents the wireless part. So ITU-T gives recommendations, gives a set of rules about how you transport timing packets over wired networks, whereas 3GPP defines how you transport timing packets over the air. That is moving forward, the next slide describes how that is done. So, like I said, as the main goal is to transport timing packets from the 5G system towards the end TSN system, we have recommendations from ITU-T about the transport part. Now for the over-the-air part, it's One of the recent solutions proposed by 3GPP is based on unicast RRC messages. That is, the G node B receives the initial timing reference from the 5G grandmaster. It now has to transport this over the air to the UE. In order for this to happen, the G node B acquires a timing reference value. It now compares this value with the end of a system frame number that it receives from the frequency of the 5G NR frequency of the UE. The G node B now transmits the timing reference to the UE at the end of a certain SFN number. There is a comparison between what the G node B has received from the grandmaster and what the G node B has received as the timing reference that it has received from the SFN. It compares both these differences, and the difference is sent to the UE as a method to correct the internal time error. So this is one way of how you can synchronize or how you can transport timing packets from the G node B towards the UE. So, so looking from an end-to-end perspective, you need to make sure that timing packets are sent on both sides or sent until the UE. And so far, I explained the different methods that are used today to transport timing packets from the 5G system towards the TSN system. Moving forward, next slide. And very recently, 3GPP in release 17, which was just released by December 2020, 3GPP described another method to synchronize the end station that are the TSN equipments, the robots that are present inside the TSN domain. What I described is how the 5G system, the mobile network, can be useful to transport timing packets from the 5G system towards the TSN. But here what is described is how you directly go to the TSN domain itself, put a grandmaster there, help collaborate, help transport timing packets from the TSN domain towards another TSN domain. The advantage of this kind of solution is that the TSN domain, the TSN operator, the players of the TSN gets the leverage. They have the control of the source timing. They take control of generating the timing packets. They manage their timing sources. It is their responsibility. Whereas the disadvantage is that the timing packet has to flow all the way from one TSN domain uplink towards the 5G system, then make a U-turn, go to the next TSN domain. This introduces delay. This introduces link asymmetries. And sometimes if you are talking about very strict, highly strict timing accuracy values, this solution may not be ideal. On the other hand, if the TSN operator itself do not want to take control of the timing solution, timing architecture, this could be one of the solutions, which is defined by 3GPP in release 17. Moving forward, the last part is the different Npn deployment options. As Joachim presented in the previous slide, again, 3GPP has defined 4 different Npn architectures. Each architecture is different from the other in a way how the RAN and the core networks are shared between the public network and the Npn architecture. So the first one, for example, and is how the Npn, the non-public network is entirely hosted by the PN. That is, I'm a mobile network operator, and we have ABB as a customer. ABB comes to Orange. ABB tells, I want to synchronize the robots inside my factory. So Orange takes complete care of what to do, how to synchronize, how to provide timing synchronization to ABB's factory wherever it is present. And this is the first case. In this case, it requires a synchronization architecture shared between the Npn and the PN. I'll go for the last one. The most extreme case is standalone network. So we have ABB and we have Orange. So ABB does not come to Orange. ABB decides for itself that it wants to deploy timing synchronization architecture for its factory. but it does not need any support from the 5G system. And therefore, in this case, it does not need any support from Orange 5G system, 5G network. ABB can have its own dedicated NPN synchronization architecture, which is in some way out of scope of this 5G smart project itself. Between the first and the last, we have two other scenarios where the first one, you have an NPN player, non-public network player, with a shared control plane and a shared RAN. That means both RAN and core of the NPN are controlled by the public operator. In this case, in order to provide synchronization, the public operator takes full responsibility because now the RAN and the core are also under the responsibility of the public operator. On the other hand, third scenario is you have a non-public network where you have only shared RAN, but the core network is not in the control of the public network. They have their own dedicated core. For this, from a synchronization perspective, it does not really change how the way the synchronization architecture and the synchronization solution is provided by the public network. The public network operator still takes control of providing the synchronization architecture and the synchronization solutions to the non-public network operator. So this slide summarizes how a 5G system can be helpful for transporting timing packets towards a TSN domain. The whole idea is to say that there are different industries that are coming up every day. There are big companies, big factories like Amazon, which do not need an operator's support to supply timing within its own factory. They are huge factories. They do not need an operator. They have their resource. They have the financial support to go and deploy itself. On the other hand, we have small emerging startups which also needs time synchronization inside this, which are present with the 50s and hundreds of robots, and they need time synchronization. And for these kind of players, mobile network operators can be really useful in order to supply, in order to manage, in order to operate the synchronization solution. So this is how a 5G system can be useful for transporting timing synchronization for a non-public network. And that concludes my part.
Right, then I provide quickly the summary. So what we have seen in this webinar now is that we have started with industrial use cases and the benefits from providing time-sensitive converged networking technology, which means both TSN and 5G are networking technologies that I'm able to support a variety of different services and still provide prioritization and deterministic behavior for prioritized services. In addition, of course, 5G provides a lot of flexibility due to the wireless nature, which means where you place devices, they can be mobile. So these benefits we have highlighted, and in practical industrial automation use cases, they play a role when we have controller to device communication, controller to controller communications, or device to compute communication types. Or both of TSN and 5G are seen as important components in the digitalization towards an industry 4.0. In order to make 5G support TSN and interwork and provide TSN compatible features, the TSN system is standardized, so that is realized as a TSN bridge to interwork with the TSN network. So the representing the entire 5G system as a TSN compatible bridge. 5G itself introduces ultra-reliable low latency communication, which means the capability to over the radio link and the core network bound the latencies of the communication and also provide high reliability in being able to guarantee latency bounds. And this can be used to match the traffic needs for time-sensitive TSN streams. From the practical point of view, TSN is supported in the control plane and the user plane. In the control plane, in the user plane, it's TSN translator functions, which are located at the mobile devices and at the network side, at the user plane function, the gateway of the 5G core network, to provide TSN capability towards the external TSN network and to map the time-sensitive communication to 5G internal connectivity based on the quality of service mechanisms used in 5G. On the control plane, there are interactions between the 5G system and the control plane of the TSN network via the TSN applications function, so which acts as a proxy between the 5G internal and 5G standardized mechanisms and interacts and translates them into the mechanisms that are used between the CNC as TSN controller and the TSN bridges. And thereby the TSN, the 5G system is configured from the CNC like a TSN bridge, and then it's realized in a 5G specific way internally. So with this functionality, 5G is able to support an integrated TSN and 5G deployment for industrial automation use cases, including the functionality that has been identified as relevant, like the 802.1 QCC configuration with the bridge reporting and configuration, the setting of 802.1 Q stick priorities, the time synchronizations that we have explained a bit more towards the end, and also per stream filtering and policing and the scheduled traffic. So this is the summary. I also, before going into the question and answers, or while we wait for the questions and answers, I also provide here a list of references of some of the reports that have been written in the 5G Smart project. Also some on the time synchronization. For example, we recently published an IEEE Communication Standards magazine paper, and then there are some other related, for example, a description of the 5G non-public networks from 5G ACIA, a summary of the interworking of 5G with time-sensitive networking that was published yesterday from 5G ACIA, to which we have contributed with our work here that is presented. And with that, I think we can go over to the question and answers.
Yes, thank you, Joachim, Krister, and Daniel. Very interesting insights on how 5G TSN combinedly can support smart manufacturing use case and how we can deploy it in the factory. We already have a couple of questions in the chat. I will go from top to bottom. The first one we have related to UE devices. When will 5G TT UE device will be available in the market, and who are the manufacturers?
Well, I mean, on this, I can maybe take this and that. Well, I mean, I think as a general rule of thumb, that is that you see in the standardization of mobile communication. I mean, the TSN translator and the support for TSN has been finished in 3GPP release 16, which was basically finished end of last year, and typically it's in the order of I would say, let's say in the order of 2 years before after that the standard is ready, that you have commercial products available which are tested with interoperability, so interoperability tested, and where you have multiple vendors aligning for this testing, and something comes to the market. Then there can be some variances depending on the complexity of the features, and also on the of course on the market interest.
Thank you, Joachim. So building on that, also we have the next question on the standard itself. Which 3GPP release completely addresses the TSN, and are there any gaps that we foresee in release 16 for TSN?
Well, in the bulk of the TSN work has been specified in release 16. And there was actually one item that was identified, and I go back to the corresponding slide, which was identified as a gap. And this is what has been addressed in release 17. And this is when the time synchronization was specified. There was the assumptions that the grandmaster clock is provided somewhere on the network side, or if I put it in the, maybe use this more, this picture here. There was the assumptions that we have many devices which want to be time synchronized to a certain master clock. And the assumption is that this master clock is somewhere provided on the fixed part of the shop floor. And it was identified with also with the discussions ongoing in 5G ACIA that there may be use cases that one may want to deploy a master clock somewhere connected to a device, which means it's now a device which provides the time sync reference, which is then transmitted via the network to other devices or to other nodes in the fixed infrastructure. And that was not part of the release 16 standardizations. That was simply not considered when the requirement was specified. And for this, an addition has been added, and this is exactly the one that is described here. And this is currently being investigated in the release 16 work. And it builds on the mechanism that has already been specified for the time synchronization that is used from the network towards the device, but it introduces now also that the originating message, GPTP message, comes from the device. So this is basically the key feature that is added in release 17.
Okay, thanks, Joachim. And now I think we have a next question on the control plane. The question is the TSN-AF and the CNC interface between the TSN-AF and CNC specified in terms of protocol, data model in any standards? If yes, which document? Maybe we can provide a reference to it.
Oops, if I unmute myself now, can you hear me? So yeah. Well, let me see what is the, I use this figure here. So the configuration of the control plane, this is basically specified in the 802.1 QCC standard. So it's in the IEEE standard, and the exact data models are specified. Well, there are young models for the data which are specified in. I would need to look it up. It's another TSN 802.1 specification which specifies those. So this is for the interactions that the CNC. The CNC is something like an SDN controller. How it interacts with all these normal, or maybe I use the other figure that I had further up here. It's actually here. It's to any of the bridges, and this is specified. So the exact protocol is not specified by IEEE, but the data models for this communication. So it could be NetConf, for example, or some network management protocol that is then being used, but the data models are specified, and this specification happens in the IEEE 802.1 TSN task group. And was this all of the question, or was there a second part to it?
No, this was all of the question. But we have more questions coming out in the chat. So the next question we have is, how do you achieve the time synchronization? PTP version 2 or GPS or both?
Yeah, so I think I can
answer
you take
that.
This. Oh, go ahead. So both of these solutions will allow you to acquire the reference timing signal. But as more and more we see problems with GNSS, such as jamming, spoofing, and then the other vulnerabilities, the most recommended solution is to make use of the PTP packets to transport timing from within your 5G system.
And maybe I can add to this. So as Daniel presented, I mean, there are basically two, let's say, there's a segment, there are two timing systems. The 5G system itself is time synchronized. And there are some reference clock, and as Daniel just says, I mean, it's PTP based mainly, that you do it on the network side, and this mechanisms for over-the-air time synchronization that Daniel also presented. And by this, you have a fully time synchronized 5G system. And over this, you can then provide any kind of timing reference by making sure that you basically correct the over the 5G system timing with the corresponding residence time that you correct for from the 5G time synchronized system. In the TSN domain itself, the protocol is being specified, and that is the IEEE 802.1 AS, which is the generalized precision time protocol that is being used there. So this is what is used in the TSN domain, but what is now added in release 17 as well is that the support for other PTP profiles are also supported in the time synchronization over the 5G system.
Thanks, Joachim, for clarifying this. Again, next question towards you, Joachim. For isolated NPN deployment, how will the private base station coordinate, negotiate with the neighboring base stations that are out of the isolated NPN? If there is no connection with the same shared core network, or otherwise if the connection is necessary for inter-base station coordination, where will the fully isolated be used?
Well, if you have this fully isolated non-public network, then basically you can deploy your network according to your own design. There's no per se coordination needed. Then there can be some variances, and that means depending a little bit on the spectrum band. For example, in some countries, if you use some of the TDD bands there, some countries regulate which TDD pattern is to be used. And in this case, basically all networks, and this would apply then for the standalone NPN, as well as for any public NPN, which are in the same band, have a common TDD pattern that is basically given by the regulator, and then they need some kind of common reference time in order to make this alignment. Here we are not on the microsecond precision level, but at least they must be sufficiently aligned with a slightly rougher precision. This can apply for some of the bands, but if you have a band which does not have this requirement, I mean, for example, a millimeter wave deployment or so, then you basically design your local system and can do this independently from an external network.
Thanks, Joachim. We have another question concerning time synchronization. Is there a need for redundancy in the case of time synchronization is lost?
Yes. In fact, if you go to that figure, the 5G system architecture, there is redundancy. Yes, yes. So there is redundancy generally. The best way to provide redundancy is to have two 5G grandmasters. I mean, this one is a very, very simplified figure. You see 5G GM sending an arrow towards the G node B, but in reality, between the 5G GM and then the G node B itself, there are so many levels of hierarchies, and you can put two different 5G grandmaster. If one fails, like let's say there is a ring topology, and you have two GMs. So if one GM is transporting timing on your left-hand side by, let's say, anti-clockwise direction, if that fails, you will have another 5G GM that is transporting timing. It will take over and it will send timing packets on your clockwise direction towards the G node B. So there is always redundancy.
And maybe if I can add to this actually, so I mean, what you, Daniel, described now very well is the redundancy of the time synchronization within the 5G domain. I think what is also important maybe to note is that, I mean, the 5G provides the capability to transmit an external time source or a timing reference over the 5G system, and it is actually multiple. So there are PTP, for example, defines different PTP domains. It's possible in the release 16 version of this standard to have up to 128 external grandmasters, which provide timing over the 5G system to their own devices. So a device is basically synchronized to a certain PTP domain. And with release 17, this increased to 256. So if we are outside the 5G system in the application domain, you can have redundancy by having two different grandmasters and two different timing domains. And these different timing domains may have also different requirements, for example, in the precision, because they are part of different parts of the shop floor operation. Some real time, so maybe some collaborative robots need very high precision if they have a more complex task to jointly perform, whereas some more generalized processes maybe are on a lower precision level, synchronized to a wall clock that is common in the shop floor.
Okay, then moving to the next question, what are the holdover requirements?
So it's a good question. In fact, if you go to the table of 900 nanosecond, so we have only now the requirements that is defined by 3GPP. I'm pointing out on this slide because I'm going to make a reference to what has been done before in the past. This 900 nanosecond is the most highest requirement that is needed today in the context of industrial Internet of Things. But if you take generally, it is 1.5 microsecond that was defined for general TDD systems. And so I'm trying to say that 3GPP defines these values, then it is ITUT that takes those values and then defines what kind of requirement, holdover requirement, budgeting, everything else comes into place after that. And therefore, my point is, it is very recent. Release 17 has just come out, and 900 nanosecond has just been standardized by 3GPP. ITUT, which is another standards group, will now take this 900 nanosecond, start budgeting, and then only will define the holdover requirements for those 900 nanosecond. So in my opinion, the answer is there is so far no holdover requirements defined for this 900 nanosecond value.
Thanks, Daniel. So moving to the next question, that is overall general to the 5G Smart project. Is any of the ideas presented today, what we had seen so far about TSN and time sync, prototyped so far in 5G Smart project or somewhere else?
Well, if I take it so somewhere else, I can say that there was a presentation at the TSNA conference recently where Qualcomm presented a trial system where they have time synchronization or 5G time synchronization. I mean, this was, I think, done, was it summer last year or so, or even earlier? Which means it was the implementation of the prototyping was done at the time when the standard was not yet finished. So probably is close to the standard. If it's exactly the standard, I don't know. What we use in the 5G Smart system, we apply some time synchronization, which is also, say, not, which is provided by uBlocks, who is a project partner. They do time synchronizations. They do it actually on an LTE system, not on the 5G system, and that is their own implementation on how time synchronization can be provided with sub-microsecond precision. That is something that we reuse. The standard is, I know that there are other prototyping activities ongoing, but the standard has basically recently been finished, which means if there are prototyping activities, they need to be aligned with to be fully standard compliant, and it's, let's say, in the progress of becoming, well, some prototypes exist, but it cannot be guaranteed that they are 100% aligned with the standard, as this has only recently been finished.
Okay. Then moving towards the next question, again on the market, can you give us an idea of the time to market for these solutions? In what year can a manufacturer plan to have a perfectly working 5G TSN solution?
Well, I mean that is a difficult question. I think the standard is. I mean, if you want to have a deployment where you have this, as I mentioned, the time synchronization provided from a device, then you have to wait until the finalization of the Release 17 standard. If we say this is not maybe the primary focus, then it's the Release 16 standard, which is basically the baseline. And as I said, it's typically in the order of 2 years from, but there are variations. I mean, that is a very rough number from when standardized features can make it to a general market adoption, but it depends also a little bit to the market demand, and of course bringing 5G now into this new use cases. I mean, there's also a difference in the market setup. The more factories are now trying to put orders into wanting to buy it, I think the faster it will go. I think that's for sure. So the market demand has an impact, but it's but now what is need to be done is that these standard changes need to be implemented, and they need to be implemented to and tested that they are interoperable, that they work with any device that implements the standard and Npn network that implements the standard. So that basically sets now the timing.
Yeah, and then we have a comment on very nice presentations. Thank you for joining, I would say. Moving forward, I think we have a question on NPN and PN. Having multiple NPN connected to public network, can you use slicing in order to provide resources to each NPN?
Well, if I take these NPN, I mean, that is one of the solutions. So that, for example, if, well, I think where we, I mean, if we have, well, either well, if you say the pointer, this option that you see here, you can have a dedicated slice for the control plane, for example, of this NPN network here, and then have the user plane, a local breakout that it stays basically on the premise. It could also be that you define a separate slice in the public network domain that it provides this non-public network service. It's also possible, I mean, I think I switched to this other slide, which maybe shows this a bit. Let me quickly check. I mean, what we showed here in the context of time syncing, I mean, you could have, think of an industrial park where you have multiple smaller shop floors of, I mean, not everything is a huge factory producing cars or so. Many can be smaller. If we have an industrial park, there could be one common 5G network infrastructure for this industrial park, and then there could be a slice, which means a dedicated service offering for each of these shop floors, which are sharing the common compound, and this could be realized then as a slice, which means they get their own control plane, they get their own user plane, and they are configured in a way to be a private network that only authorized devices are entitled to access this particular non-public network.
Yeah. Then moving forward, we have a question on limit on the number of UEs. Why there is a limit on number of UEs that can be synchronized? I mean, as I can sync 10 UEs, I can do the same for 1000 UEs. I think that refers to the SA1 standardization requirement that we have on the slide.
Right. Okay. Now I think you refer to where were the requirements? They were somewhere here. Exactly. I think here you mean that it says. I mean, there is no limitation, but what this is now an SA1, which means it's a specification which provides the framework that is used by other groups in 3GPP in the standardization of saying, well, this is the targets that we want to be able to achieve. It doesn't mean that you that you're not allowed to support 301 UEs or even 30,000 UEs. What it says is that the standard groups that specify the details of the solution should make sure that at least this one here can be supported. So if they would do some evaluation, then this specification here creates a little bit of a reference case that could be evaluated and validated.
Okay. Then the next question that we have is, do you know about any open source CNC or CUC application?
Passing this maybe to Krister, do you know anything?
No, not to my knowledge. Not on top of my head. No.
I believe in the TSNA conference, for example, that there are, for example, some academic or research institutions, I believe, are using something. I don't know if it's fully open source or so, but I think there are some frameworks which are used in the TSN research domain. How open they are, I cannot answer. How generic they are, I can also not answer. So I guess it would need to a little bit further investigation by someone Googling this.
Yeah. Thanks, Joachim. Then moving forward towards the test bed question, what type of 5G network and devices do you need to test TSN right now, like in Aachen or Bosch?
I mean, we have different types of test beds deployed. So they have different frequency bands. For example, the one that we use in Chista uses millimeter wave. The ones in Germany use the mid-band 3.5 gigahertz band. And then which means it's different devices which support the corresponding bands. So this is what needs to be tested. But I think the general market is that I mean, network components as well as devices typically support a subset of the different frequency bands that are enabled with 5G, and it's a little bit country specific as well, which of these combinations are being used. And if you know where you want to, in which network you want to deploy your device, then you have to make sure you have a device that supports these bands. But they are the standard bands, but not all devices support all the bands. But typically there are devices which support, for example, the market-specific bands of a certain region. I don't know if this was exactly the question that
I think the question referred to TSN also, to test TSN features. Yeah, I think we can move forward now to the next question. Which standard addresses fault tolerance, redundancy, etc.?
I mean, that is a very broad question. I mean, fault tolerance is, I mean, for example, if we go purely in the TSN domain, then this mechanisms of 802.1cb on frame replication and elimination for redundancy is a way for defining or for replicating or defining redundant TSN streams. That is a standard which does this in a TSN specific way. There are some parts in the 3GPP specifications which also describe on how redundancy can be supported from a network perspective. But to a large extent, redundancy and resilience is also something that is which is an implementation specific question on how to build how to build products that they have redundancy support.
Okay, then moving forward, we have another question on would TSN-based 5G network have issues with sharing network with other slices in the network slicing function?
I mean, the principle of slicing is that you can isolate different users. You can basically specify different slices to be rather independent and make use of a common infrastructure. And of course, you have to make sure if you have to provide guarantees of a certain resources item to a slice that this is not violated. You cannot have as many slices as you want on the common infrastructure. You need to make sure that the promises that you make in the slice specifications are supported in the resources that are provided by the infrastructure. But in principle, it's possible to have a slice which is for TSN kind of traffic, and then on the same infrastructure another slice.
Yeah, also to add here, within 5G Smart, we are investigating this issue right now, and I can assure you that in future webinar we will provide some aspects, some insights towards these aspects also. I think that's okay. So we have another 2 more questions. I think we are already reaching the time limit. Maybe we can answer them offline as time is already over now. With that, I would say thank you for joining the webinar. With that, I would say let's conclude the presentation. Thank you again and have a nice weekend. Bye-bye.
Thanks, everybody.
Thank you all.
Bye-bye.